Welcome to Hot Chips 24. Keynote 1, the Surround Computing Era.
All right, time to get started again. It's a really great pleasure to welcome Mark Papermaster, who is the Senior Vice President and CTO at AMD. Mark has had a distinguished career of over 30 years in engineering leadership. He started at UT Austin, where he got a Bachelor in Engineering, and then a Master's at the University of Vermont. Then he went to IBM, where he was a member of the technical leadership team and oversaw the development of several of the key microprocessors and blade system for the company. From there, he moved to Apple, where he was the vice president responsible for the hardware development of iPods and iPhones. Then to Cisco, where he was the vice president responsible for silicon engineering, and now at AMD as the senior vice president and CTO. Mark is going to tell us about AMD's strategy around the era of surround computing. Mark?
Thank you, Christos. Thank you, and it's a pleasure to be with you at the 2012 Hot Chip Symposium. This is a great conference. This is where really every year you get the best and brightest out of the chip industry, academia, from industry, coming together, and I think you're getting as much out of the presentations as you are in the sessions in the hallways when you all get to talk and compare notes and look at the trends. And that's exactly what I want to talk with you about today. It's about the trends that we see at AMD, and frankly, some changes that we think are quite significant. So when you talk about change, it's almost trite. You say, we live change every day. That's, we're all technologists. That's the nature of what we do. We bring change. But what I'm really going to describe to you is, our sense that, of course, there's change in the industry. You're seeing more and more vertical integration. You're seeing, a lot of the hardware through the software solutions being brought together in tighter and tighter ways across multiple segments. And that has a profound change. We're seeing changes in technology. We, of course, have integration year after year where we can put more and more on device. But how that integration is occurring is different. It's been changing where started off, frankly, in consumer with the system-on-chip approach where you could bring more and more functional elements together. And you're seeing that trend now permeate across a multitude of segments. And it's not just the functions that come together from a traditional sense of computing, it's the sensor capability that's coming either on board or at a very, very low cost, low power. And this combination of technology, of this continued trend for integration, and this advent of very low cost, very low power sensors is really a change in terms of what can be done to what I call fundamentally change how we interface with computing. And that's really the advent of this term, surround computing. And so, I want to set the stage first a little bit by what we mean as I say, all of this change in environment of devices and technology. Let's step back first and just recognize what's going on with that information, with the internet, that we all, are using day after day. It's an integral part of our lives. But let's just look at some of the data behind that. When you look at the environment that we have right now, it's a convergence. The convergence has occurred from how we live our personal life, how we live our business life in terms of our expectation of computing. We want our data, not just any data, our personal data, whether it be work or personal, available to us anywhere, anytime. We want it across any of the devices, whether it be our smartphone, our tablet, our PC, across accessing any of our information, photo library, business presentations, it has to be pervasive. We expect to be connected wherever we go. And that is driving a huge change in terms of the data processing that's required. I throw some stats on the slide here with 245 exabytes of data. That's 10 to the 18th bytes of data. The last stat I show is 2010. It's actually projected to be 400 exabytes this year of data crossing the internet. But just to show you that rate of change, you know, in 2010, when you hit that mark, that was more data than had been traversed over the internet in the entire history of the internet coming up to 2010. And so it just tells you that, you know, that we're on this meteoric explosion of data, projected to be at a zettabyte by the end of 2015. I don't have to look any further than, you know, my day-to-day, and I think your day-to-day, when you look at the amount of data that you're processing now versus last year versus the year before, and it's growing. You see it, I know if I look at my family, it's a digital family. My kids do everything online. It's sort of an anachronism for them to think about, opening up that printed textbook or getting that newspaper. We don't have a newspaper come to the doorstep anymore. It's all digital. And, you know, that amount of data that we're just relying on flowing across the internet, coming to each and every one of the devices that we use, is having a significant impact. And if you look at the data center, look at the projected demand of, really greater than 10 million servers in 2016. I mean, it's just a phenomenal explosion. And how we're accessing that server data is changing dramatically. It's not all the big box server providers. It's highly tuned data centers for cloud workloads that you're seeing emerging. So change in technology, change in the industry, change in the infrastructure, right? And so what I want to talk to you about is, where we are in that progression from my standpoint of how we're interfacing to the computer. Interaction, we've had it for over 10 years. I mean, it's, of course, we expect that highly interactive engagement, and it's been improving year in and year out. Now we come to expect that as we interface with computing, it's not the keyboard and mice. Of course, you still use that. But, for a lot of your content absorption, you're expecting to have a very visual experience. In fact, you're expecting to have a touch screen more often than not. How many times have you been on that plane with the screens on the back of the seat, and it's sort of a transition point? Some of them are touch, some of them aren't. I always laugh when I see the ones that aren't touch, and you see, folks are really not sure what to do as they touch it and they can't get a response. That's our expectation, is changed interface. We see that, as well in the visual experiences. We expect to be able to have incredibly rich visual interaction, 3D cinematic experiences, not just at the IMAX theater that you go to, you expect it in your home, right? So for the last 10 years, our expectations have grown significantly as to how we expect to interact with computing. And you know what? Our expectations don't ever go down. We grow them at leaps and bounds. And that's what's going to happen now in this era of surround computing. Because as those devices, as those computing devices and those sensors permeate around us, we're going to have a situation where it's basically a data overload and an interface overload with traditional means. And so you're starting to see the cusp of that change. You're starting to see that voice recognition, right, that you have on a Siri, a Google Voice. You have gesture recognition you might be using with your Microsoft Connect. So we're starting to see this change. But when you look at our expectations, we're gonna absorb this change as rapidly as the technology can provide it. We're gonna want to have a very seamless experience with computing, because it's the only way we're going to be able to absorb all of that data, the useful data that's being collected around us. And that brings me to, really this, definition, I say, of this surround computing era, right? This is where we will be, already from the platforms we are today of that smartphone, that tablet, the PC, we're going to see a further explosion of the platforms. You see experimental devices out there today, eyeglasses. You see it in your thermostat. You see it in your your appliances at home, your refrigerator, right? So we're already seeing computing going into any multitude of the devices or of the interactions that you have over the course of the day. And it's becoming very fluid in terms of that interaction, right? Again, it's not the keyboard and mouse anymore. It's a much more natural interaction that you're starting to build on with those devices. And in this new era of surround computing, we want anticipation of our needs. Again, we're at the cusp of this transition. When you look at that anticipation of needs, what do you do when you want to go to a restaurant? If you've got a smartphone with a GPS, which I'm sure most of you do, you're having that smartphone that already knows your location, tell you the restaurants in the vicinity. You might even use the voice interaction to say, tell me the restaurants nearby. Tell me where the nearest movie theater is. But it's pretty rudimentary in those interactions. You're needing to ask a very specific question, and oftentimes you get the result back and you throw your hands up and say, that's not at all what the question I asked. I love the ads for some of the voice recognition. I wish it was quite that advanced in the capability, but it's moving rapidly. This capability is advancing at leaps and bounds. And so that's what we're seeing. We're seeing the environment that we live in, the expectations that we have bring a new era of computing. And for those of us who are technologists, it puts an onus upon us to continue that rate of innovation, to bring this era on. It has profound implications. It affects our thinking and our actions and our development in the whole client environment, that point of interaction, and has equally profound interactions on the back office, on those server farms, on the cloud, right, on the computing that's being done at the back end. So it's it's really going to affect the whole spectrum of computing. And I want to take a minute and just talk through some of these workloads that we at AMD see emerging. We see them growing. We see them enabling the kind of interaction that I described. And it really is bringing to bear that natural user interface that's been described for some years. Mark Weiser. Mark lived here in the Bay Area and was the chief technology officer at Xerox Spark. Xerox Spark just put out such phenomenal innovations. And to paraphrase a quote from Mark, said that basically profound technology changes become almost invisible. They weave into the fabric to where you don't, at the point you look back, you don't know, where was that technology? I don't see it anymore. It's basically become invisible. That's where the interface to computing is going. It will be, rather than that mouse and keyboard that you have today, rather than the rudimentary interfaces that we have today, it'll be woven in the fabric. It'll be seamless. It's the stuff of science fiction of yesteryear, of 2001, A Space Odyssey, or even the recent Iron Man movie, right, where you've got that type of seamless interface. It's not the distant future. That change is upon us now, right? And that technology that's enabling this is going to be growing at leaps and bounds. Let's talk about why that is. What are these workloads that allow this type of seamless interface? I start right off the bat with natural user interface in gesture recognition, right? Today it's touch. You touch the screen. You're pinching, you're zooming, you're moving. You're still going to want gesture. You will not touch. But you're going to see, as the advance of technology, your fingers won't even need to touch the screen, right? You're going to have that sensing when you're off the screen. Likewise, the gesture recognition will become more and more natural as you get more sensors, more processing capability behind that sensor data coming in. You can anticipate the real meaning of your gestures in a very natural way rather than very prescribed fixed motions that we have today. So it's going to be very, very enabling. Let's talk about biometric recognition, biometric devices. We've had for years, been developing in an AMD and in our heritage. It's been, a huge investment in terms of all of the graphics visualization. So, that's taking a model and rendering an image. And it's a tough problem, and it requires very significant compute. But when you look at this biometric recognition, it flips that problem on its head, right? Because what you've basically got to do is take an image and translate that to a model and use that model and run algorithms to match it. So that's facial recognition, retina matching, all of the more advanced biometric recognition techniques are a very computationally intense exercise to achieve the kind of real-time, accurate results that you will be expecting moving forward. Augmented reality, to me, I just find fascinating because of this obvious trend of all of the computing around us, because of all that sensor data around us. It's this explosion of data that now is being amalgamated, at the server. That data is available. What do you do with it? How do you make that useful? And we're coming now to a point where you truly can have, over time, as we develop this kind of computing capability and bring it down to cost, a real augmented reality, where in those devices, that multitude of platforms that we talked about a moment ago, you can have that useful data sent down to you, morphed onto the very images that you're interacting with, whether it be, overlaid images, whether it be on the screens that are around you. You can have that anticipation based on the context of where you are, what you're doing, what friends are around you. I mean, the amount of information that's available as you traverse your day and can be, again, amalgamated, analyzed, brought back to you is simply phenomenal. Actually, it's a little scary. But I look at it, and it's going to be very exciting. Even before we get to that vision of a full augmented reality, look at some of the near-end gains that we're going to see as we progress down this era of surround computing. Content, making it easier to manage our content, getting at that high-density data, high-density graphics, enhanced audio capability, having that seamlessly transmitted in a much more robust way to this multitude of platforms around us. I say, beyond the HD experiences, as you can have really, we've used that term surround sound for many years, but in surround computing, you can have a complete experience, rich graphic, rich video, rich data experience around you beyond HD. And content management, today, typically a very serial process is you go to Netflix and you're looking for your movie. You might be going in your photo album, and looking through, finding your favorite album you want to go watch. But from a content management, where we're going, if you look in this trend that we're on, this era that we're transitioning to, that becomes much more seamless. That whole interface. Again, I'll make that analogy to the movie Iron Man that is one of my favorites, where you're scrolling through data with gesture recognition. You can look at your library, look at the images, pick what you want, select it with emotion, watch that movie in an immersive experience. So the kind of capabilities that we're looking at are really game-changing in terms of how we interact with the computing. But we can't get there today. We're at this without significant improvements in how we get the computing done. And that's where acceleration is required. You need accelerators to be able to use both at this client level, right, where you're at that point of interaction, and also at the cloud. Because you're not going to do any of what I just described to you. You're not going to touch it unless, one, it's preserved your privacy. huge issue for our society today is maintaining your privacy. You've got to know that you've got that trust of where your personal data, where your work data is being managed. This plethora of information has got to be protected, and that's at that central point. Again, that data is shared across all of your platforms. It comes together at the cloud, and at this backbone of computing, you've got to know that you can have trust of your privacy. Secondly, that cloud has got to provide the context. When I said there's this overload of sensor data that's going into the cloud, that's all managed. It's all got to be managed. It's got to be sorted. The analytics have to be run so you get useful information back. Lord knows we get enough inundation of data on our day-to-day walk of life. So it's got to be managed. You've got to be able to filter it. You want the right context, the right information at the right time. And then thirdly is basically that client offload capability. If you want the kind of capabilities, that seamless interaction that we're just starting this trend to in this era, then you've got to have deep analytics available to you at the cloud. You've got to be able to do robust searching algorithms, robust indexing. You've got to be able to go through hordes of data, yet you've got to do it in an affordable way. It's got to be low power. Data centers today are very constrained. So it puts a tremendous challenge on the kind of technology that we need to provide as a community to the client and to the backbone, the server, the data farms. So I want to, as I go into the cloud, and I talk about this overload of data that's come together. I talk about is managing all of that unstructured data. And the fact is that with all of these connected devices feeding this data in, it's driving a real change in terms of data center requirements. They've got, to already, it's been that you've got to have scale. So you've got to be able to, in a very modular way, add on computing at a rapid pace to be able to grow as you're having more services you're providing, more connected devices you're supporting. But you've got to do that in such a way that you support these new workloads. These new workloads, again, are largely parallelizable. It's the only way that you can provide that type of, as I say on here, real-time response, because you need to have a low latency for this interface to be effective. You've got to be able to have a consistent security architecture, and you've got to be able to provide an efficient way to bring this computing to bear, and that's dense servers. So I'll talk about each one of these as I go through our approach at AMD and our thinking about how to solve this problem in a very unique way, a very innovative way. Our thinking is that when you look at surround computing and you look at how it places these demands on both the client and the server, that it is very clear. The only way that we're going to get the kind of multiple-fold increase in efficiency is to accelerate that parallel workload through heterogeneous engines. It's not new to leverage heterogeneous engines, a CPU, a GPU, other accelerators. We've got examples of phenomenal supercomputers out there today that are doing just that. They're solving the world's most difficult problems. They are providing amazing virtualization, amazing graphics, visualization capability of masses and masses of data. But it's extremely expensive, and it's not going to enable this sea change of how we day-to-day interact with the computer, because it's got to be brought down into a very cost-effective, basically, supercomputing for the masses for us to get through this change, for us to really enable a surround computing era. And so what we'll talk a little bit about, our thinking in terms of how you do that. How do you augment that change? How do you bring that change on? And what we're doing is we put out there this year the Heterogeneous System Architecture, HSA. And what this is a construct to do just that, to bring that change in by aligning us in the industry as to how we go solve that problem. We all know that you know, when you have academia and industry going 10 different ways, you're going to get a lot of innovation. But does it really move the ball forward for the industry? The only way that happens is when you get critical mass, when you get a broad adoption. And that's exactly what heterogeneous system architecture is going to do for acceleration. What it does is really allow applications to much more fluidly, much more effectively access those accelerators. You know, as I gave the examples of the national labs, the big supercomputing centers, they've got very dedicated programmers, very expert programmers to be able to unlock that value. They're attacking workloads that are very specialized. They've got specialized library calls that they do, and it's you know, it's very unique coding that they're having to attack the problem set with. With HSA, our goal is very simple. Unlock that value to the ISVs, to the software developers. Unlock it by letting them use the programming languages that they're already using today. Open this up to the high-level languages, or the, you know, and you know, C, C++, you know, with the web, with the JavaScript, HTML5. Open this up, make it easy to program. Put a common application interface, application programming interface in place, so that you have many programming targets coming to one application interface, and align us in the industry as to how you can create engines underneath that. There's lots of room for differentiation underneath that, but without a common application programming interface and a common path from high-level languages to exploit it, you will not see this sea change. You will not see this broad adoption, because it's going to take a long, long time to get meaningful applications to bring this to bear. So that's what's fundamentally different with our approach at AMD, is to invest, but to bring the industry with us, to align us to bring those applications. And you'll see that when we do this, it makes the world very different for the programmer, because it allows them, by using the language constructs that they already have today, to be able to write one program and have it be optimized across the CPU and GPU or other accelerators without low-level programming, without directing, right? It's going to recognize the parallelism, be able to do this, and more importantly, I call it being a pointer as a pointer, not having to manage in software the memory. It's a shared memory in this heterogeneous system architecture. It's a huge deal for the programmer. It's a huge deal for performance, as you're not moving data sets across memory and burning all that power and taking all that time as you move across. It's a tremendous performance improvement. And so when you have that type of coherency, and eventually in the heterogeneous system architecture, a true full context switching, then you achieve this full capability of heterogeneous system architecture, which will really enable these applications to grow and to bring the kind of change that I described to you earlier into each of our daily lives. We've done this as an industry-wide initiative. We announced this last quarter, and it's been very well received. In fact, stay tuned. You'll see upcoming announcements as others are joining on board this approach. But let me walk through these benefits that we see with heterogeneous system architecture. First and foremost, it's power efficient. Because you're optimizing the workload based on whether it's scalar, based on whether it can take advantage of the parallelism, and very seamlessly moving it back and forth, you're going to get an inherent power efficiency advantage. Shared memory, power advantage, right? I talked about it being easy to program, right? This is what's going to drive the application set over the topic. And certainly future looking, as we look at the trends of the workloads, the type of data analysis, whether it be big data and the analytics and the servers, or whether it be the face recognition on our client device, this architecture's future looking. It handles CPU and GPU. It'll handle other specialized accelerators that we come up in this industry going forward. And it's open standard. We've established a technology foundation with Heterogeneous System Architecture Foundation. You can go to hsafoundation.org, and you'll see that we've put this out there as an open standard. Again, this is our commitment at AMD. We believe that open is the way to success. We've seen this time and time again when you want to change an industry. You've seen what Linux did in terms of opening up any number of server and client applications. That's what HSA Foundation will do in terms of accelerated computing. And we're seeing that industry support. We're seeing others come on board, right? And as you see that momentum build, and you see the ISVs adopt this common application programming interface, that's where we get the momentum. And I want to talk to you about how at AMD we're bringing this to bear, starting on the APUs that we've already been shipping. The kind of technology that you're hearing about at this Hot Chips. You heard about what we've done on some of our low power optimizations with Jaguar cores. You will hear about our Trinity APU and our graphics Core Next architecture for our next generation GPU architecture right here at this 2012 Hot Chips. So I'm going to take a few minutes and just at a high level talk about our approach with APUs. I want to talk about some enhancements we have in our third generation core, STEAMROLLER, our high performance CPU core. And I want to talk about as well some of the innovations we're driving in power optimization and how we bring the system solutions together. So start off just talking about the APU. We look at the APU as that natural engine to start this movement of heterogeneous system architecture, start this acceleration of creating a capability, an infrastructure that will support this surround compute era. Because it is a breakthrough enabler. We've shipped over 30 million APUs already today that as they bring that CPU and GPU together, provide an incredibly power efficient, very high virtualization, very high graphics capability effort, along with the CPU effort, seamlessly brought together on a single die of silicon. So we've been at this for some time, and what you'll see us doing now is taking that next step of having our APUs line up with the heterogeneous system architecture and provide that hardware that can bring this change on, provide that optimization for the programming community to leverage this, and the APU will be the platform of choice for acceleration. So what I want to do now is dive down a little bit and talk to you a little bit, about some of our AMD investments and innovations. Before I do, I'd like to just take a moment at this Hot Chips Symposia to pay a tribute to a dear friend of mine, Chuck Moore, that passed away this year. I can't go through this talk without mentioning Chuck. Chuck was so instrumental at AMD, such a key leader, but such a key leader and influencer to the industry. He served on the Hot Chips program committee, and I can tell you, I feel the energy here as I milled about, and I can tell you, Chuck would be very proud of the talks that are on today and the innovations that each of you are bringing to bear. So, I think all of us, feel Chuck's presence with us, and we're in constant memory of Chuck within our AMD community. Chuck was one of the innovators of the Bulldozer family, which I'm talking about here in our third generation of STEAMROLLER core. And what I want to describe to you is the approaches that we're taking. It's before I go into detail, I mean, let me start with the original design point of Bulldozer. Bulldozer was designed to be an outstanding virtualization engine, an outstanding compute engine, to be able to run at very high performance. As you see in the diagram, it's designed to have a core pair with 2 dedicated integer pipes and a shared floating point unit. So in our third generation, we push this forward. We keep all of those attributes that we have with the Bulldozer family, but we drive efficiency. You talk in computing all the time. You got to feed the core. You got to feed the beast. So it's about how do we feed that engine more efficiently. It's about improving the integer and floating point pipe execution itself, and it's about performance per watt, energy efficiency improvements that we have done with this third generation steamroller core. So let's jump in and talk about some of those changes. First and foremost was it's about throughput. It's about preventing stalls. So we had a shared decode. We doubled the bandwidth of that decode so that we have dedicated decode engines for decode logic for each of our integer pipes. So this is a significant improvement in terms of our throughput. We've made changes to the iCache. This one's pretty straightforward. I've been at this for years, like you have, and you've got to at every turn look at how you can reduce those iCache misses, and the changes we made give us a 30% improvement. The other thing we've done is really improved as well our instruction prefetch. We've increased the size so that we can have a greater prefetch capability, and as well to be able to recognize loops more efficiently and prefetch them. When you add it all together, it's a 30% ops per cycle improvement, quite significant, and we're realizing that benefit as we run workloads and traces through this core. This core has completed the design phase, and will be in silicon and shipping in systems next year. The second I want to talk about is improving that core, improving that execution across the pipe. So first and foremost was register files. We made a set of changes, tuning not only the number of entries in the register files, but really just tuning our access and our scheduling around it without any impact or reduction to the latency. So, really tuning up that integer execution, and really also improving the low latency that went with this. We have had improvements that we've done for our data cache. Again, more throughput through the execution pipes, and as well we've improved our store to load forwarding. We took 2 cycles out of our store to load forwarding. So, a number of improvements that we've made to be able to feed the core, within the core itself to improve its efficiency, and then lastly, to ensure that we have more energy efficiency. And so what we've done there is really optimized across the board for our average power dissipation. Several changes that we did within the microarchitecture itself. One of the things we did was a better recognition of the loop behaviors. Particularly, you can look in with iFetch, if we look at on our micro-op buffer, where we recognize that we've already loaded a loop, we'll reduce power dissipation by recognizing that, not going back to the iCache, but leveraging that loop right out of the micro-op buffer. In the floating point, we've not only streamlined our execution across each of the floating point pipes, but we've looked at how we had it organized and made it more efficient. No reduction in terms of the floating point operations per cycle, but we are more effective where we had our FMAX, 2 separate FMAX, 2 separate MMX units. We've dropped one of those MMX units because the workloads, what we found, aren't running both of those simultaneously. And what we are actually doing with our workloads is where you have a high need for MMX instruction set execution, we have the dedicated MMX, and we leverage one of the FMAX to be an augment. Where it's FMAC intensive, you've got the 2 dedicated FMAC pipes as we had before. So we save about 25% area, and in the workload analysis that we've done, we see that we've maintained, and in fact, because of the power efficiency, improved our performance. And then lastly, we've got an innovation around the L2 cache, and it's power management. It's about turning on the iCache as we come in and out of hibernate to make it smart, to make it look at the workload and turn on section by section of that L2 cache as it's needed. based on the workload. So a number of improvements that we've made across STEAMROLLER, our third generation, and we'll be excited to bring that out to market next year. Okay, shift gears a little bit and talk about low power. Look, whether it be in the cloud, whether it be in the client, everywhere that we're, embedded devices, anywhere we're putting our products, our technology, low power matters. We all get that. And it's about necessity that you expect. You expect whether it be that client device to have a longer battery life and make it through your plane ride. It's about running cooler for a data center. It's about being simply fitting the amount of computing you need in this floor space that you have. So it's, for servers, it's all about lowering that total cost of ownership. That's the only equation that matters in a data center. And so our approach to low power that I want to talk to you about, some innovations that we've done here, is multifaceted. It goes beyond the process technology. Of course, you need to take the benefit of a node-to-node technology transition, but that can't be where you bank your innovations. That can't be where you're going to deliver your value at the end of the day, given the trends of the semiconductors node technology. So what we've done, I'll walk you through about three different approaches that we've taken. One, coming at it from a system standpoint, really leveraging the hardware and the software, how they're working together to manage power. Secondly, innovative on-die power management that we've deployed. And then thirdly, a very different type of design methodology that we're doing on our AMD processor designs going forward to get a much more efficient implementation of our processors. Okay, diving in. So first, I show one example here, a motion DSP, a typical graphics application, doing a cleanup of a video that we all might be doing on our laptop, on our mobile device. And here's this example of hardware and software coming together, and it's a heterogeneous system architecture example. It is an APU with a CPU and a GPU, and so first you get this benefit, about 20%, simply bringing that together, sharing the memory, getting that physical benefit. But when you stack on there the hardware improvements that I described to you by having a direct interface, a much more efficient interface from the software into the CPU and the GPU, and being able to switch based on the workload back and forth in between, you end up with a multiple-fold increase. In this example, it's a 4x improvement in terms of the efficiency of getting this piece of video through its routine and running that enhancement. And so again, this is an example of these emerging workloads, the kind of performance efficiency benefit you can get as you bring that hardware and software approach together and attack it with a heterogeneous system architecture. Second approach I want to take is a very fine-grained approach that we did. In fact, we've deployed this in Trinity, and you'll hear more about this from Sebastian. But it's being able to very actively manage where you're raising the voltage, where you're raising the frequency, and where you're lowering it based on the demand of the application. So we have many sensors placed throughout our die. We're constantly looking at where the workloads are. We have a 32-bit microcontroller that's amalgamating this, pulling this together, bringing the smarts onto the device, and shifting and sloshing around the voltage and frequency to the GPU, to the CPU, or balancing it simply based on the workload, right? What does it need? So it's just it's a smarter way to to be adaptive and to look at the workloads and to manage the power efficiently. I can tell you it has huge ramifications. You look at Trinity, the APU that we announced this year and have been shipping since early this year. You'll see it in these ultra-thin configurations. It's a 17-watt performance. So the same device that can be in a mainstream computing, you can leverage the power management, bring it right down into a 17-watt TDP and have it in a beautiful ultra-thin PC laptop configuration. So very empowering as you apply these techniques. And then the third innovation I said was a design methodology approach that we're taking, a different a different tack. And so what you see up above is a piece of our bulldozer. It's actually a floating point unit. This is the practice that we applied for many, many years at AMD. It's hand-drawn, it's customized, it's fully optimized for performance, and it achieved all of those objectives. But the demands on us right now aren't just to get every last megahertz of performance, but to do it in such a way that you've optimized for the lowest power, for the lowest space. Because again, in a system-on-a-chip approach, it's all about what's that combined set of functions that you can integrate on the silicon and run most efficiently. So we've adopted a high-density library that we're rolling out across our designs at AMD. And with this new library approach, combining this dense library along with very sophisticated automated place and route routines, we're getting a tremendous area and power savings, really up to 30%. And what that does when you roll this together at the chip level is a 15 to 30% lower power when you're in a power-constrained environment. And that's like a technology node's worth of energy efficiency. So, it really takes the approach for design now of thinking from a stack level across the hardware and software and how they interact, how you manage on the device, and then thirdly, these design methodology approaches. It takes bringing all of that together to truly optimize our design approaches going forward. So the last thing I want to talk to you about is just that, rolling all of the various enhancements together and attacking from a system level that point of optimization. And the example I want to talk to you about is basically fabrics. So another key change that you see going on in the industry is tremendous focus about how you take the point processor and APU solutions that we have and bring it together very, very efficiently. At AMD, we were last year working on this approach and brought C-Micro into the fold. There was an acquisition of C-Micro in first quarter, and it was a great marriage of technology, bringing a very, very efficient fabric that can bring basically supercomputer architecture of interconnecting devices down to the masses, bringing this in a very cost-efficient way to data centers. And so it can add masses of processors and do it in a very, very efficient way. Let me go into a little bit of detail here. So call this the AMD Freedom Fabric. And what this freedom is freedom from the overhead, frankly, of traditional server compute. So what you're able to do is bring together with this fabric a virtualized I/O capability, a virtualized fabric capability, a very common interface, a PCI Express interface, which is very commonly used, very easy to bring together and link these nodes at a phenomenally lower total cost of ownership. So you can link today hundreds of nodes together, in the future thousands of nodes together incredibly efficiently. And with the virtualized I/O and storage capability, you shrink the amount of real estate needed to provide the solution, and it's incredibly flexible, right? In fact, we found as we brought this in, so we're bringing our AMD solutions to bear. It's actually ISA agnostic. We can apply this to all of our solutions in terms of CPU, APUs, different ISAs. This is a very flexible, very high-performance fabric that we're deploying as a part of our IP portfolio, and we're moving pretty quickly with this. When we did this acquisition early this year, we said in the second half of the year we'd be dropping our Opteron solutions onto this with this fabric, and that's exactly what I show you. This is a server node. You're looking at less than 12-inch, a full server node of the processor, the memory, and the fabric needed to interconnect with the hundreds of other nodes that you can put together in a dense server format for incredible efficiency. Some of the servers that are being shipped at a quarter of the power to 1/6 of the floor space of previous generation server approaches. So it's a very exciting technology, and this approach of very efficiently bringing solutions together, leveraging all of the innovations across not only the base compute structure, but efficiently bringing I/O and storage, very low overhead, is going to be a tremendous game changer to attack the kind of emerging workloads that will need this efficiency. So what I want to do is bring to a close, wrap together some of the thoughts that I shared with you, the direction that we've been on at AMD, and really summarize by, as I say in the title, it's not a pure speeds and feeds race. It hasn't been for the last several years. It's really about how you bring the solution together. How do you solve today's class of problems, and how do you solve tomorrow's class of problems much more efficiently, in a different way, really take into account the requirements, the emerging workloads. And you have to have a system view. If you look at everything that I walked you through today, it's from the point of view of the application. That's what matters. It's the application that you're running, and how do you make it more efficient? How do you accelerate that application stack? Once you do that, once you solve at that highest level how you're bringing that difference to bear, how you're bringing that acceleration, then you've got to do it efficiently. And what we're doing at AMD is creating a very ambidextrous, a very flexible, agile delivery approach in our SoCs, really leveraging the differentiated IP that we've been developing over many years. And so that's where it comes together. It comes together from an AMD standpoint of being there for the next wave, of enabling this surround computing era by bringing what today is available in a very expensive approach in supercomputing really down to the volume of the client, the volume of data centers. And we're going to do that and accelerate this transition through, first, the heterogeneous system architecture. If you don't have the applications, if you can't bring the programmers to bear over the problem, then you're not going to make a dent. It's going to be a proprietary, siloed solution. So first, heterogeneous system architecture. Secondly, flexibility. I coined the term ambidextrous, left-handed, right-handed. We're going to be ambidextrous in everything we do. HSA is ambidextrous. It'll work with the multitude of computing solutions that you put underneath it. Our approach, our system-on-a-chip approach of putting our solutions together will be ambidextrous. The fabric by which we interconnect each of those will be ISA agnostic, will be ambidextrous. So you've got to have flexibility in the approach that you take. You've got to be able to interconnect this with this very efficient fabric to be able to get scale with these solutions. And you've got to maintain, and we are maintaining, as I've showed you today, a relentless focus on power management. So we're very proud at AMD to have had a strong history of innovations, of bringing advancements. If you look at over the years of 64-bit computing, of integration that has brought just tremendous performance advantages to the industry, and we're continuing that train. And the way that we're continuing that train is looking ahead to the endpoint as to where the applications are going, and how do we unleash the power of heterogeneous computing for this wave of parallel workloads in the surround computing era. This is our investment. This is where we've aligned our IP, our approach to our APUs and the silicon investments we're doing, how we put it together at the system level, and how we enable our customers and the consumers to have far more productive solutions, and frankly, at the end of the day, to change the way that we all interface with computing, the way that our lives are productive over the course of a day in this surround computing era. So with that, I want to thank you very much for having me here today. I want to conclude my remarks. I think we've used up the allotted time, but I will be here if there's questions. Feel free to come down. I'd be happy to talk to you. Thank you very much.